Have you ever wanted to build your own integrated circuits? Or maybe try your hand at replicating the first room temperature superconductor? Well, if you're like me, you've probably thought, I can't do that in my garage. I need a multi-million-dollar cleanroom laboratory for that. Well, actually, if you're not trying to build the latest and greatest CPU with a billion nanometer-sized transistors, then semiconductor fabrication actually can be done in your garage. Most of what you need is readily available, either from hardware stores or online shops. You can even buy blank silicon wafers from Amazon these days. While some equipment will always be out of the reach of hobbyists, some equipment is actually easy to build at home. Stick around, and I'll show you how I built my very own tube furnace. So, first things first. What is a tube furnace? Why would you want one? And why would you want to make your own? A tube furnace is a special type of oven normally found in laboratories or industrial settings. Unlike your oven at home, which maxes out at about 300 Celsius, tube furnaces can reach temperatures of 1000 degrees Celsius or higher. But the thing that makes the tube furnace really special is in the name. The tube, where material is heated, can be sealed at the ends and gases pumped in or out to precisely control the atmosphere inside. At high temperatures, oxygen from the air can react with your product and contaminate it. In a tube furnace, oxygen from the air can be displaced with an inert gas or removed altogether with a vacuum pump. Tube furnaces are also useful when you want reactions to take place. By adding a very small amount of an impurity gas, you can precisely modify the electrical properties of a silicon wafer, creating the transistors that make up an integrated circuit. Laboratory tube furnaces can cost tens or even hundreds of thousands of dollars. The cheapest tube furnace I was able to find was about $3,500 new and about $1,200 used on eBay. That's a little bit out of my price range, so I'm going to make my own. My starting point will be this $20 quartz glass tube I bought on McMaster-Carr. Quartz glass is a must because it can withstand higher temperatures than regular glass. For the heating element, I'm using 22 gauge nichrome wire. I'm looking for a total power of about 800 watts, which in this case corresponds to about 10 to 20 feet of wire. To prevent the tube from losing heat, and to prevent the surroundings from catching on fire, we're going to need some insulation. For that, we're using alumina ceramic wool. Lastly, we need some kind of a glue to bond the heating element to the tube and keep it from shorting out. I'm using sodium silicate refractory cement, which starts out as a paste, but hardens into a glass at high temperatures. The first step in construction is to wind the heating element around the tube. I'm using a plastic rod suspended between two anchors to hold the tube. This will allow me to rotate the tube freely as I wind the nichrome wire around it. I'm using a paintbrush to apply a thin layer of refractory cement. This layer goes between the coil winding and the tube and will soften during the first firing. This gives the coil winding a little bit of room to contract around the tube if needed. If you don't have this layer, then when the nichrome cools, it can tighten around the tube and shatter it. I discovered this when my first tube developed radial cracks exactly where the nichrome wire was touching it. It's also possible that these were caused by thermal stresses, but at any rate, when I started applying this layer, the problem cleared up immediately. Now I'm using a paper towel to clean up some of the cement on the ends of the tube. Now I'm putting the tube into an oven at a relatively low temperature of 100 Celsius. This dries the cement so that I can wind the coil over it without it sinking in. Such a low temperature is necessary to avoid creating bubbles during the drying process. Be patient and wait at least 2 hours to take it out. Now comes the tricky part of the build, winding the coil. The most important thing to do is to make sure you anchor the ends thoroughly. I'm winding several turns of wire and then securing it with blue painter's tape. You really don't want this to come undone and ruin all of your work right at the very end of the winding, so make sure this is on tight. Now wind the coil, maintaining an even spacing and keeping the wire tight. My goal is to wind about 40 turns of wire around the middle 8 inches of the tube, so I'm keeping about a 1/5 of an inch spacing between turns. This is the easiest time to fix problems, so don't be afraid to unwind a little bit of wire and correct mistakes as you go along. Once you're satisfied, anchor the far end in the same fashion as the first. Now that the winding is complete, apply another coating of refractory cement. I'm using just enough to barely cover the wire. This will keep the windings in place. I started out by using a paintbrush, but I very quickly realized it's faster and easier to just use your fingers. Make sure to use gloves while doing this though. Sodium silicate is a caustic material that will give you chemical burns. If you happen to upset the spacing between the coils, you can very gently nudge them back into place. This will be the last opportunity you have to get this right, as the next step will solidify the cement and lock the coils into place permanently. Now it's time to remove the tube and take it to the oven to dry. A couple more hours in the oven, and this tube should be ready for action. Now that the tube is dry, it's time to cure the cement. This will require heating it to about 1000 degrees Celsius for a couple of hours. I realized that I probably made a mistake leaving the tape on, because it's hardened in the oven and now it's difficult to remove. I think next time, instead of tape, I'll use aluminum wire or some other means of securing the ends. For now, I'll just pick away at the tape slowly and attempt to undo my mistake. I found that I was able to use a razor blade to remove the tape, seemingly without scratching the tube. Hopefully I don't pay for that one later. I then rolled the tube in 2 feet of ceramic insulation, and honestly, I'm not confident this is enough. I pressed on anyway, and used some soft aluminum wire to keep the insulation from unrolling. For this test, I'm using a variac to control the power, but the final design will use microcontrollers and solid-state relays. I sacrificed a power cord and wired it up to the heating element. I then turned on the variac and started ramping up the temperature slowly. I inserted a high-temperature thermocouple directly into the tube to keep track of how fast the temperature is rising. For a quartz tube, it's important to keep the temperature ramp rate to about 30 degrees Celsius per minute maximum. This is a little faster than I would like. For a while, it won't really look like anything is happening, but at around 600 degrees Celsius, you'll start to see a slight orange glow coming from the tube. After about 30 minutes of heating, I finally reached 1000 degrees Celsius. The tube is now glowing bright orange, and I'm starting to get some hints that the amount of insulation I'm using is probably not enough. You can see the orange glow from the tube coming through the insulation. Right now, the exterior of the insulation is only about 250 Celsius, and it's resting directly on a scrap of wood, so the way I see it, as long as there's still moisture in the wood, I'm not going to have any troubles, but once that's gone, we're definitely going to have a problem. Yeah, that's no good. Hold on a second while I cool the tube and air out my workshop a bit. Alright, well, the tube is cooled off. Let's check the damage. Ouch. I'm probably going to have to use more insulation than this. I added another inch of insulation, and I'm now resting it on a cast iron pan instead of a block of bare wood like last time. I once again brought the tube up to 1000 degrees Celsius, and it looks like the exterior of the insulation is only about 150 degrees. That's roughly 100 degrees Celsius less than before, so I think that's pretty good. Something I found interesting was just how well contained the high temperature air is. Even though it's a staggering 1000 degrees Celsius on the inside of the tube, the air right outside the tube is actually not that hot at all. I can hold my hand in front of it for quite a while before it becomes too hot. I then slowly cooled the tube back down to room temperature. Unfortunately, at around 500 Celsius, I started hearing some worrying sounds coming from the inside of the tube. I am really hoping that's not the sound of another quartz tube cracking. To my surprise, though, the noises were coming from the thermocouple and not from the tube. Well, I can't say I've ever seen that before. This thermocouple is supposed to be rated for 1000 degrees Celsius, but I guess that's a lie. This is what I get for trusting Amazon listings. I found a new thermocouple on McMaster-Carr rated for about 1250 degrees Celsius, so I'll replace the original one with this. Back on the workbench now, I'm going to unroll the insulation and check how the tube is doing. You can see how the high temperatures have converted the grainy sodium silicate cement into a shiny glass, and the heating element is now embedded inside. I can see that a few of the coils are a little bit too close together, and I'm pretty sure that was just an error when winding the coil and not a problem during the firing. I'll be a little more careful next time. Alright, time to switch things up and make the body of the tube furnace. I'm using a piece of 20 gauge steel and a sheet metal bender I bought at Harbor Freight. I'm marking the locations where I'm going to bend the steel, creating a 5 by 5 by 12 inch chamber. This is where the tube and the insulation will go. I'm relatively new to sheet metal construction, and I gotta say, I'm impressed by how quick and easy it is to put a relatively simple part together. I was able to do all of this with just this bending tool and a small bandsaw. In the future though, I'd really like to get a proper bending brake, a rivet gun, a spot welder, and maybe a plasma torch. You know, just the essentials. Anyway, that's the main body of the furnace finished. Now on to the other pieces. Now I need to create 2 end caps, one for the front and one for the back of the furnace. I cut out the corners on the bandsaw and used the bending tool to bend the tabs inward to create the caps. I also used the same method to make a door for the bottom of the tube furnace where you load the tube. Then I did a lot of sanding and filing down sharp edges. Take your time doing this because 20 gauge steel will really cut you up if you leave a sharp edge behind. I know that one from experience, unfortunately. Here are all the finished sheet metal pieces. Now, if I had a spot welder, this thing would go together really quickly and easily. Sadly, I don't have one of those, so I'm going to do the next best thing. I'm drilling a ton of holes and using sheet metal screws as fake rivets. Now, if we're being honest, I probably used about 4 times as many screws as was really necessary. But you know what? That's what we call a 400% safety margin. Now that the whole assembly has been screwed together, it's rigid enough for me to drill 2 holes, one in the front and one in the back. I'm using a 1.5 inch hole saw, that way I'll have a little bit of wiggle room when aligning the 1 inch tube. I drew a little crosshair so that I could align the 2 holes properly. I cannot stress enough the importance of promptly deburring every new hole you put in sheet metal. Deburring as you go, instead of at the end, means you have a much better chance of not cutting yourself. Now that everything has been assembled, and the fit has been checked, and the parts have been sanded, we are finally ready to paint this. Which of course means that now I have to remove all 60 or so screws holding this thing together. I wasn't sure how hot the exterior of the tube furnace would get, so I decided to play it safe and use barbecue paint. This stuff is pretty insane and is rated for something like 1,000 degrees Fahrenheit. The only downside is, I think this paint needs to come up to a really high temperature or else it's too soft and it's easily scratched. If I did this again, I think I would use engine paint instead. Engine paint can't withstand quite as high of a temperature, but it also seems to be a lot more scratch resistant than this barbecue paint. Alright, it's been a couple of hours and the paint is dry to the touch. Time to install the insulation and the tube. Rather than rolling the tube, like I did last time, I'm cutting out rectangular pieces of insulation and stacking them. Just a reminder that alumina is very high on the hardness scale, and so any scissors you use to cut this stuff are going to get wrecked. Also, this stuff forms a very lightweight abrasive particulate that floats in the air, so make sure to wear a dust mask. I had to do a lot of different test fits with different thicknesses of insulation to try to center the tube in the hole. This stuff is compressible, so you're going to be chasing your tail a little bit to get it perfectly aligned. I left a lot of nichrome wire dangling off the ends of the heating element, but we definitely don't want that. Cut the wire short and replace the ends with copper. You can just twist it together, there's no point in soldering it because the solder will just melt anyway. Once the tube is back in, all remaining insulation layers get a small slit cut in them so that the wire can pass through. My plan is to have the wires come out the bottom of the unit, so I drilled a couple of holes into the bottom plate. I need to make sure that these bare copper wires don't short out against the metal of the bottom plate, so I'm using some thick heat shrink wire as insulation. I'm expecting the body of the tube furnace to be about 200 degrees Celsius, which is about the upper limit for heat shrink insulation. I think a better idea would be to use wires with a high temperature insulation like silicone. I didn't have any of that on hand though, so I decided to go with heat shrink insulation for expediency. Once I reinstalled the door, I used a multimeter to verify that the resistance of the coil was still about 15 ohms and that there were no short circuits. Then I installed all of the sheet metal screws yet again. I think in the next version of this furnace, I'm going to have a separate door with like 4 sheet metal screws, so that way I don't have to take everything apart every time I want to change the tube out. Alright, it looks like the body of the tube furnace is finally done. I'm wiggling the tube a little bit to check that it won't slide out. The tube can move a tiny bit, but it's clearly not going anywhere, so I don't have any worries that this tube is going to fall out. Now I need some kind of a base to mount this on. I have a spare piece of melamine wood from when I made this countertop, and I think that'll do nicely. I've oriented the body how I think it fits best, so I'm just going to mark it and start drilling holes. There's no need for this to be perfect, and honestly, I might just replace this board anyway. Now all that's left is some kind of control panel to go along with it. I ran out of 20 gauge sheet steel making the body of the tube furnace, but I have some 16 gauge sheet steel lying around, so I'm going to make the control panel out of that instead. Now, 20 gauge sheet steel is a walk in the park to bend. But 16 gauge sheet steel is another thing entirely. So I'm cutting some slits in the bend points to give myself a little bit of an easier time with it. I drilled all of the mounting holes and cut out the opening for the LCD before bending it while everything is flat and easy to work with. I once again made sure to deburr and smooth out all of the sharp edges. Bending this piece into shape was not easy, but I got it done in the end. On the plus side, 16 gauge sheet steel is so thick that this thing doesn't really need any reinforcements, it's plenty strong as is. Once again, I just kind of figured out where I wanted it and marked and drilled the holes. Now, up to this point, I haven't really said anything about the electronics I'm using to control this tube furnace. The reason for that is that the correct way to do this would be to just buy an existing ramp soak controller. A ramp soak controller will not only control the temperature set point, but it will also control the rate of change of temperature. This is critically important because, as mentioned before, quartz tubes can't really tolerate a ramp rate any greater than about 30 degrees Celsius per minute. Any greater than that, and you risk the thermal stresses slowly cracking the quartz tube over time. I didn't use a ramp soak controller because I wanted to learn a little more about PID loops, so I busted out an Arduino and wrote my own code for this. I'm not really going to go into any detail on the code. If you want it, I'll make it available as a link in the description of this video. For this project, I'm displaying all the relevant information on a small LCD. We've got current temperature, the current ramp rate, and elapsed time, and the general state of the machine. I installed the LCD, Arduino, solid-state relay, and the rest of the components into the console. I'm also installing grounding wires to each of the metal components of the shell. That way, if there's ever a short between the tube and the chassis, it'll just blow the 10 amp fuse instead of becoming a fire or electrocution hazard. My new ceramic thermocouple came in, so hopefully I won't have to worry about shedding little bits of metal inside my tube anymore. Alright, moment of truth. Everything is assembled and ready to go. It's time to take her for a test drive. Today's destination is 1000 degrees Celsius, and we are ready for launch. It's been almost 30 minutes now, and we're about halfway there. I'll see you back in another 25 minutes or so. Alright, we've hit 1000 degrees Celsius. There's been no problem so far, so let's do some science. I've got a small scrap of a silicon wafer here. Let's see if we can grow an oxide layer on it. I bought this small quartz boat, and I'm just gonna put the silicon wafer in it and slide it right into the center of the tube furnace. I'm using a stainless steel rod to push it into the center because, the tweezers obviously aren't long enough. Now, you can grow an oxide layer in air, but it'll go a heck of a lot faster if there's a little bit of steam in the tube as well. To accomplish that, I'm using an Erlenmeyer flask on a hot plate with some glass boiling beads and filling it with deionized water, about 200 milliliters or so. I'm using a rubber stopper and a right-angle glass tube to redirect the vapor into the tube furnace. Then I just crank the heat and wait for things to start boiling. You want this thing to be just barely boiling, so I'm checking with my hand to see if I can feel a small amount of steam coming out. Once I'm satisfied with that, I wrap the whole thing in just a little bit of aluminum foil as insulation to help hold in the heat. Then we just slide it into place so that the steam is entering the tube. 45 minutes have passed, and it's time to check the results. I'm using the stainless steel rod again to carefully push the quartz boat towards the other end where I can just grab it with the tweezers. I'm going to let it rest for a couple of minutes because even when the quartz isn't glowing, it can still be really hot. That thing is probably still 500 Celsius. Alright, it's been a few minutes. Time to take a look and see what we've got. Under some sunlight, you can see that there is this beautiful blue hue across the surface of the entire wafer. That color isn't actually the color of silicon dioxide, which is clear. It's the color of the light interfering with the very thin layer. The thickness of the oxide layer and the color you see are directly related, so you can actually use this to determine what thickness we have. This blue color corresponds to about 320 nanometers or so. Well, that was a great success. The furnace has been running for a couple hours now, and the exterior temperatures aren't even that hot. Looks like the insulation is really holding up. I guess that means it's time to push this thing to the limit. This quartz tube is rated for a maximum of 1200 Celsius, so that's what we're shooting for. Any higher than 1200 and the tube will soften and risk warping over time. Well, after a few more minutes, we made it to 1200. I'm not going to say that the tube furnace likes being this hot. It's a little bit unstable. I might have to work on the code. But as proof that it can reach this temperature, I think we've succeeded. This is by far the highest temperature I've reached in my shop. I had to turn the camera exposure down so that the tube wasn't just a blinding ball of white light. 1200 Celsius is about the highest temperature that you're going to need for semiconductor fabrication. Anything above that, and you risk melting the silicon wafer itself. I then slowly ramped the temperature down to about 400 Celsius. This is the point where it's pretty safe to just turn the heater element off entirely. At this point, the insulation alone is sufficient to keep the temperature ramped down slow enough to prevent damage to the tube. I'll just let it chill here for a bit until it's back down to room temperature. Well, it looks like everything works. This furnace should be more than adequate for some basic semiconductor experiments. I plan to use it for growing oxide layers, as well as diffusing dopants into silicon in order to make transistors. There are a few upgrades I have planned for the tube furnace, such as a longer tube and vacuum/air fittings to properly control the atmosphere inside. For now though, I'm looking forward to using it to create my first semiconductor device, a PN diode. I want to sincerely thank you for sticking around to the end. If you enjoyed this video, please like and subscribe to my channel, and if you want to contribute to this project, consider checking out my Patreon, Projects in Flight. See you next time!